All right, Steve, go ahead with your questions about the homework.
Okay, so in chapter 10, one of the questions has to do with power curve. Is that something we should do, like make a graph in Excel, or just like make a data table with sample values?
Was it really that? Which one is it? Which problem? 10 what?
Question 10.106, part B.
Oh yeah, yeah. Yeah, you could pick like 3 values would be good enough for that. The
Okay.
3 values for an alternative mean, and then determine what the power is for each one of those, and then just graph it. 3 is good
Okay.
enough. Yeah.
The other question is in chapter 11. You in the email it says to assume an unequal variance for questions 11.78 and 11.80. So far, I've only tried 11.78, but in that problem, it says assuming that the standard deviations are the same.
Which one is it?
11.78.
78.
Yes. It's the third to last line in the question, like last sentence, basically.
Well, that one I didn't. I believe I'm letting you. I'm not saying for that one. Am I?
I have the email. It's oh, you know what? Your parentheticals are after it, and then there's 2 more, another parenthetical, and then 1 more. So I guess it's before the. So yeah, what you wrote in the email is
All right, that's fine. Just to know the
it could be interpreted
78.
as applying to the things that just came before or the things that came after, and I guess you meant the things that came after.
Yeah. Well, I don't know. Let me. Maybe I was tired that day, but 78 has its own information. It's the other two.
Yeah,
The
that
other
makes
two.
more sense.
The other two don't even specify it. If you look at the other
Right.
2 problems, that's why I made you make those assumptions, right?
Right. The email itself says chapter 11, pages 404 to 406, 1178, 1180, assume unequal variances, 1188 to 1190, assume equal variances, 11.92. So the way that it's in order is that assume unequal variances could apply to 78 and 80 or 88 to 90. And that's where I got confused. I just assumed that it would apply to 78 and 80.
All right.
But which one is it referring to?
All right, hold on 1 second. Hold on. Let me check my email for that. I don't know. I think I wrote it right. I have 11.78, comma, 11.80, assume unequal variances, comma.
Right, but
11.88, comma, 11.90 without a comma. I put assume equal variances, comma, 11.92. What's wrong with that?
Well, 11.78, the question says to assume equal variances.
That's right. I didn't say anything there.
Oh, okay.
I didn't say anything there.
I see what the problem is.
Yeah, I mean,
so
every other problem, I put the parentheses next to the ones where I want you to make an assumption. That's all. Put that right
okay.
after.
So you're. I see.
That's not
All right.
unusual. Why would?
No,
I
that's
think
my
everybody
mistake.
does that.
I thought that I thought it applied
No.
to the 2 that came before it.
No, there's a comma there. I put commas in between the ones that we do. The parentheses comes after the one without the comma.
Right. Okay. I have one more question.
Yeah.
When we are making,
Yeah.
let me see. When we're making, sorry. You know what? Never mind. That's all. Yeah. If I can think of the question I had, I'll email to you.
All right, all right. Well, thank you for the question, Steve.
Sure.
Uh,
Sure.
All right. Now I just posted an Excel file in Canvas that we'll use for demonstration today for pretty much everything. It's the one that's used actually throughout the chapter. And you'll see it. It's in today's. I just posted it like a minute ago. So if you want to download it onto your computer, the Excel files for chapter 15. Do you see it for this week's module?
Yes.
If you could just download it so that you can upload it into Minitab when we get to it. All right.
Is it CX15 DEX?
Yeah. Yeah. It's the only one that's there. That's the one I want you to like do what I do as we go through today. So and actually, if you want, open up Minitab and just
Oh, you know
load it
what? I do remember my last question.
All right, go ahead.
In chapter 11, the examples that we did in class, we usually just use Minitab, but if we want to show our work, should we just do them by hand or do like some kind of Minitab related thing?
You could, well, you mean in terms of showing your answer? Minitab will probably be correct. Like which problem? Give me an example.
11.78, I guess. That's the only one I've tried so far.
Well, what you do is you just pull out Minitab doesn't give you the answer. Minitab just gives you the data, right? The summary statistics.
Mm-hmm.
So just state that you got this from Minitab and whatever you got, and then answer the question.
Okay.
See what I'm saying?
All right. Sounds good.
Yeah.
Yep.
So you could just summarize what Minitab told you, the information the Minitab gave you, and then write up the answer, and that'll be it. That's all you have to do for each one of those, actually. You can't use Minitab. Let me think about this a minute. Oh, no. I'm thinking of the quiz. Forget about what I was just about to say. If you haven't seen the quiz yet, then you'll know what I mean. You can't use Minitab for the quiz. All right. The quiz, by the way, you can work on after you've completed the homework, since the homework's due tomorrow, right? Isn't it true? Wednesday? Yeah.
Yes.
And then Friday, the quiz. There's only one quiz, so that's due Friday. And then we'll talk more about the project, the mini project. It'll be worth like 5 homeworks or something like that, little project. I'm thinking like 50 points for the project. Right? I'm going to give you a data set, and you're going to be working on things that you're learning in chapter 15. It'll be a bigger data set than this one. This one only has 6 observations. All right, that's not even a data set. I don't know what you would want to call it. It's a baby set. I'm going to give you a real data set that you'll be able to load into Minitab, and then you won't be able to do anything by hand because the data set will be too big. So you'll have to use Minitab's features to do it. You could do it in Excel too if you wanted to. All right. Anyway, let's get back to
Can
chapter.
I ask a question?
Yes, another question. Yes, please.
Because I feel like we do the regression questions based on the Minitab a lot. I mean, is it sufficient for us to use Minitab for the exam?
Of course. I've always said you could use Minitab for the exam. Minitab's available to you. It's an open book, open software. Open software meaning Minitab.
I mean, if it's sufficient, maybe you will ask some question, Minitab cannot work
Right,
out, or
Minitab can't answer, right, right. I'm aware of what I can ask that would be, that you couldn't use Minitab for,
okay.
yes. So assume that that might be on your test next week, there could be problems where you can't use Minitab and you have to figure out another way of answering it, like through a formula or something.
Okay. Okay. Gotcha.
You'll see it on the quiz too. There's a question on the quiz like that where Minitab's not going to be very helpful.
Okay.
All right. So let's share the screen. See, I did start the recording. That's good. So let's go to, oops, I don't see the textbook. So, unfortunately, the way Zoom works, you have to actually highlight the tab that you need to, it won't open up multiple tabs at one time. So there we go. Kind of annoying. There we go. Can you see it? Can you see the textbook?
Yes.
Yes.
Right. So we went through the introduction to what regression is, right? We went through the equation last time and talked about some of these topics here, residuals and homoscedasticity, heteroscedasticity. We talked about this idea that at each value of x, that there's the distribution of y is considered to be normal. That's one of the assumptions, right? So normality, and then this idea of variance being about the same across every the variance of y is about the same across all values of x, and then the y values are statistically independent of one another. That was the other one. We talked about how we use calculus to come up with what's called a least squares equation. And this is it here, where we can predict y based on a particular value of x, and where b1 is the slope and b sub 0 is the y-intercept. It says it right here. We call the least squares a criterion here. So that's the methodology for doing this. And what does it do? It minimizes the sum of the residual square. Just what you're seeing inside the parentheses is the residual, right? The actual value of y minus the predicted value of y, which is based on the least squares equation. The difference in each of those values is called the residual, and we square each one of them and then add them up. And the best fitting line, the least squares line, is the one that minimizes the sum here, the sum of the squared residuals. So that's the whole idea. Remember, residual is the vertical distance from the point to the line. Any points below the line, the residual is considered negative, and any point that's above the line, that distance is considered to be positive. All right, and then these formulas, these are derived from calculus, and this is the formula for the slope of the least squares line, and this is the formula for the y-intercept of the least squares line. And you do need the slope first before you get the y-intercept, since the slope is part of the y-intercept formula. Okay, and then this is the data set that you just downloaded, this one right here, where the x is some score in a dexterity test and y is your productivity, right? Hourly productivity, how productive you are in producing a certain product. And they show you how to come up with the slope and y-intercept using formulas. And that's the equation and the graph of the least squares line. y-intercept's 19.2, slope is 3. Now, the way to interpret this, by the way, getting back to high school, because this will come in handy later, is that for every change in x, let's say x increases by 1 unit. Can somebody tell me if x increases by 1 unit, how much does y increase by?
3 times the unit, 3 units.
Yeah, but 3 units, exactly. Whatever the units of y are, it increases by those 3 units. So 1 unit of x, whatever it's measured in, an increase in that increases the y by 3 units. That's exactly right. This 19.2 gets canceled out in that calculation, right? So that's not part of that calculation. You increase x by 1 and you increase y by 3, right? That's actually the definition of slope, isn't it? It's the way slope is defined. And we use that definition when we want to estimate a value of y based on a particular value of x. It's not in the data set. Point estimates using the regression line, that's exactly what they mean by this. If we pick an x that's in the range of the x's that are in your data set, but that particular value of x is in itself not in the data set, then we can just plug it into the equation, replacing the x with that value, like 15, and we come up with an estimated value of y. That's literally what regression does. Regression is a way of predicting a value of y based on an x that's not in the data set. Right? That's what they're doing right here. So 15 is a score on this dexterity test, and your productivity is measured in number of units per hour that you're producing, 64.2 units. Now, this prediction is based on a linear growth. Would you agree with that? Linear growth.
Yes.
Right. Well, not everything grows in a linear way, right? Sometimes we have exponential growth. Think of the COVID virus, right? Growing, its impact growing exponentially throughout society. So there's other types of growth besides linear, but this is what a simple linear equation allows you to do. Allows you to use linear growth to estimate a dependent variable based on an independent variable. Okay, so this is called linear growth. All right, and of course here's the line right here. Now, this part of this, now this is some output from Minitab, all right, which I'll explain a little bit later. This thing in the middle, ANOVA, is something we did not cover. It's actually in, I think, chapter 13. Yeah, that's called analysis of variance. Typically, that's not covered in a first semester course in statistics. It's usually second semester. So it's unfortunate because it should be covered in the first semester. If you're going to cover regression, you might as well cover ANOVA too. So this ANOVA piece here, we're going to ignore it because we didn't cover that chapter. And we're going to pay attention to regression statistics, and also down here, coefficients. All right, coefficients, and also there's some statistics based on the coefficients here. Some of these terms may sound familiar to you. For example, standard error, t-statistic, sounds familiar, right? P-value. Here's a lower 95%, upper 95%. These are confidence intervals. So all of these things don't have to be used for means and proportions. They could be used for anything. Anything that we're estimating, we can test to see if they are significant or not. In other words, if they're different from 0. All right, and that's exactly what these are showing here. These are indicating tests that we can do on these coefficients. What are coefficients? Those are the intercept and the slope. All right, those are estimated using calculus, right? So there are ways of testing each one of these to see if they are significantly different from 0. All right, so the null hypothesis would be, for example, that the slope, this DEX score, when it says DEX score here, it's referring to the slope. So the null hypothesis is that the slope, the beta, is 0. And the alternative hypothesis is that it's different from 0. It's something different from 0. All right, could be negative, could be positive. All right, and then you have your t-statistic, which will test whether whether we can reject the null hypothesis. And then we have a p-value here, which we can use and compare it to alpha, right? If we have an alpha 0.05, p-value is 0.012, we can reject the null hypothesis that the beta for this equation, the slope is 0, and we'll say the slope is significantly different than 0. That means we feel comfortable using it in this equation. Does that make sense? Sort of make sense? All right, this is the Minitab thing that you end up getting, but we'll look at that in a minute. Remember, this book is 9 years old, so the Minitab, there's the more versions of Minitab since then, and Minitab may look a little different than when the way the book is looking at it. Then they do give another example here. By the way, these examples here, we could easily enter this into our Minitab, couldn't we? We could open up a new Minitab spreadsheet and literally just type in these numbers. Type in one column, call it X for year. We could call it year, X is equal to year. And the next column is Y is equal to shares. We create our own regression based over this, right? We could do that too. Not a bad exercise after I've gone through what we're going through today is actually try this. Try this 15.9, see if you what you end up getting in terms of the output. But maybe that's something we'll do on Thursday. Thursday, we're just going to do problem solving. We're going to take Minitab and we're going to go through it and see what it gives us. Here's another one right here. Here's another possibility, right? There's boat sales and boat trailer sales, right? So, so maybe the X is the boat sales and the boat trailer sales are the Y, right? Here's another one. Something that deals with movies. All right, anyway, we'll just move on to the next section. Now, before we actually look at the output today of that really simple looking data set, let's talk a little bit about the idea that we could estimate a standard error for our Y's, right? Now, we've always talked about standard errors in terms of one variable, right? Talked about it. We have one variable and we find the standard error, right? Which would be the standard deviation divided by the square root of the sample size, right? That was our formula for that. But here we have a regression where we have Y that's dependent on X, right? That's what they mean by Y dot X here, is that Y is dependent on X. The dependent variable is dependent on the independent variable. So we want a measure of the variation of Y based on X. And that's called the standard error of the measurement, or standard error of the estimate, right? That's another way of saying the same thing. And here's the formula for it. It's easy to calculate. If you don't have too many data values, you can easily do this. And well, you could do it, I guess, no matter how big the data set is, you can do it in Excel. What it is, it's the Y's, each Y value minus its what? Its predicted value based off the regression equation. So this Y minus, what is Y minus Y hat? This is a little hat above it. What is that equal to again? What is the one word that describes that?
Variance?
No, it's not the variance, just the Y, just the what's inside the parentheses here. The Y, Yi minus Y hat I. What is that called? What's the word for it? Starts with an R. Next letter's E. Next letter's S.
Result.
Next letter I.
Residuals?
That's right, residual. That's right.
I don't recall the word.
All right, residual. Remember, the residual is the difference between the actual y and the predicted y, right? It's that vertical distance that I've showed you before. So the numerator is the sum of the residual squared. That's that measurement we talked about that determines what the least square line is, right? That we want to minimize that. That's the numerator, the sum of residual squared. Now it's a square root here. What's the denominator? Can you tell me what this denominator represents? I know it says n minus 2, but don't tell me that. What does it represent? In your own
Degrees of
words,
freedom.
degrees of freedom, right? And why is it n minus 2, not n minus 1?
Because the number is dependent on two variables.
That's right. Well, not two not two variables, two things that are being estimated. All right. What are being estimated? The slope and the y-intercept. So two parameters that are being estimated, not the x and the y, but the parameters. So the two represents two parameters. The beta, which is the slope, and the beta sub 0, which is the y-intercept. And you'll see this in when we actually in chapter 11 we saw this, didn't we? We saw when in the pooled variance, the degrees of freedom was n1 plus n2 minus 2, right? So you could see that the degrees of freedom can change based on how many variables that you have. All right. So this is called the standard error of the estimate. All right, that's the standard error of the y's based off the x's. So it's easy to calculate it, all right, because this is a nice way of setting it up, by the way. If this is your equation up here, and here's your dexterity scores, right? Here they are. And then you know what your y's are for each one of them, because that's given what the y's are, the productivity. Then you calculate y hat for each of the x's, right? You just plug in 12 for x here, and you get your 55.2. Plug in 14 here, you get 61.2. So you can figure out all of the y hats and then subtract them. Okay. By the way, if you add up all these residuals, what do you end up with? Well, let's see, 1.6, negative 1.6, 0.2 plus negative 0.2 is 0. Remember, I told you the sum of the residuals are 0. That actually shows up sometimes in my final exam questions. What's the sum of the residuals in regression? And the answer's got to be 0. One of the answers I could give in that multiple choice question is, what do you mean? I don't know. That's not enough information. Right? Most students will check that as the answer. But the answer is 0. So that's why you square them. So you square each of these residuals, you add them up. That's your numerator, by the way, of the what? What is this called again? SY dot X. What is that called? Standard error of the estimate. All right, standard error of the estimate. So plug all that in. 22.80 divided by 3, because there's 5 data points. Minus 2 is 3. You get 2.757 units per hour is your standard error. All right. So for a regression, the standard error is going to look different than for a sampling distribution for one variable. All right. Completely different calculation. Now, based on this, the standard error, you can come up with a confidence interval for the mean of y given a specific value of x. Remember, we don't, this is a sample, right? This is a sample. This information about y and x doesn't come from it's not the whole population, it's sample data, right? Sample of x's and y's. So we don't know what the mean of y really is, or the mean of x. We can just estimate it from the sample, correct? So what if we wanted to create a confidence interval for the mean of y given a specific x value? All right, given a specific x value. How would we do that? Here's the formula. Well, it's a t. We're going to use, remember, a confidence interval has a critical value and a standard error, right? Typically. But in this case here, there's 3 components that are multiplied. You have your t, you have your s, the standard error of the estimate, and this standard error of the estimate has to be multiplied by something. It's this square root thing here. Now, what you are doing, I have to make it really clear here, is that inside the square root is 1 over n, which is a sample size, 1 over the sample size, plus you have this fraction here. The numerator is, you have to be given, to come up with this confidence interval, you have to have a specific value of x for this, all right? So there's confidence intervals for each one of the x's in your data set. Can you picture that? If you have, in this case, 5 data points, you're going to have 5 of these confidence intervals, each one of them for the x that's given. All right. So the numerator is going to be that x that you're picking, one of those 5 x's, minus the mean of x, the quantity squared. So it's a deviation of that x from the mean of x squared. It's not the sum of anything. It's just that one value of x. It's being, you're subtracting the mean from. The denominator is where you're using all the data. For example, the first term in the denominator is the sum of x squared. So each one of those x's are going to be squared, and then you add them all up. That's the sum of x squared. Minus, you have the sum of x, so that's all the x's added together, that quantity squared divided by the sample size. So this division here is just for the second term here, not for the first term, right? So you take this fraction and add it to 1 over n and take the square root of it, and that you're multiplying by the standard error of the estimate, the thing that we just calculated, and then we're going to multiply it by our t critical value. How many degrees of freedom in the t critical value? In this case, what's the degrees of freedom?
N minus 2.
Give me a number. How many numbers in this data set? How many values in the data set? Let's look at it again. Here's the data set. So what's your degrees of freedom?
3.
3. 5 minus 2. Right? So this would be a t, right? T distribution with 3 degrees of degrees of freedom. And if it's a 95% confidence interval, then you would use that critical value, right? Where the area to the left is 0.975, just like we've always done. And the degrees of freedom is 3 in this case. You have to be careful because we've always said n minus 1. It's n minus 2 here for degrees of freedom. Whoops. Cursor's doing all sorts of funny things here. And it even says it right here. T value for a confidence level desired and degrees of freedom n minus 2. So the key here is that you can create a confidence interval for each one of these values in your data set. Now, can you set up, what if I had not 5 values in this data set? What if I had 1,000 of them? And you were doing this, let's say, now, we'll have to see if Minitab has the ability of doing confidence intervals for each value of x. We have to see if it can do that. We know it can create a confidence interval for the betas, right? But this is for the x, this is for the y's. Here we're coming up with confidence intervals. What if Minitab can't do it? How would we do it in an Excel? Well, we would have to, for each observation, right? We would have to have this formula. And we have to make sure that it points to that particular value of x, right? So we can do it. We can do this. Can you picture we can do it? And then copy the formulas all the way down. Even if we had 1,000 observations, it wouldn't matter, right? long as you had the formula right and you're pointing to the right value of X, it wouldn't matter, right? It wouldn't matter. So we can create confidence intervals very easily in Excel based on this formula here. And notice that what's being added and subtracted to, y hat. It's not y, but it's y hat. The estimated value of X is what we put in the middle of our confidence interval. All right, and we're adding and subtracting from it these three terms here that are being multiplied. Okay, so that's it. And it's doing an example of it right here, but we could easily do it in Excel, right? Easily, instead of trying to do it manually. If you had 1,000 observations or 10,000 observations, obviously you're not going to do this manually for each one of them. All right, so that's called the confidence interval for what? For the mean of X, for mean of Y. It's estimating the value of Y for a given value of X, right? It's actually estimating the mean of Y given a specific value of X. That's what you're really estimating, the mean of Y. And this Y hat is just an estimate of the mean, right? All right, and so you're going to have a confidence interval for each value of X, but it's not giving you a confidence interval for that particular value of Y. It's giving you a confidence interval for the mean of Y. What if I wanted a confidence interval for that value of Y itself on that observation, that particular value of Y that's in your data set, all right, for that line on your data set? Then you come up with this formula. And this formula, wait a minute. This isn't it. This is the confidence interval formula. Look at this formula. It's exactly the same formula for the I guess you would call this the margin of error, this term that you're adding and subtracting to Y hat. The difference is you have an extra term in here, 1 plus. Everything else is the same. You just have 1 plus, and you have a 1 in here that's added to what you saw before inside the square root. This makes the interval a little bit wider. All right. And this is called a prediction interval that you're creating, prediction interval. And it's giving you the confidence interval around what? It's giving you an interval which predicts where that actual value Y would be inside that interval, the actual value of Y, right? So it's a prediction interval for an individual Y. That's what this is called. And it looks exactly the same, except there's a 1 plus inside the square root. Everything else inside the square root's the same. Everything outside the square root's the same. It just has a different interpretation. All right. So let's look at the interpretation for the previous formula. This here. It says, based on these calculations, we have a 95%. We have 95% confidence. They forgot the word confidence. That the mean productivity per person scoring 15 on the dexterity test will be between 59.919 and 68.481 units per hour. It's in other words, if we had unlimited number of people, all right, who scored 15 on the dexterity test, and we averaged all of their productivity values, we would have 95% confidence that that value, that average, would fall somewhere between 59.919 and 68.481 units per hour. Okay, that's what it means. However, for the prediction interval, let's look at the interpretation. It's going to be a wider interval, a little bit wider. All right, that's because of that 1 plus inside here makes it wider. It says for this applicant, all right, so let's go back what it said before. It said the mean productivity for all people, right? This is saying For this applicant, we have 95% confidence that his productivity as an employee would be between these two values per hour. For this applicant, for this one person, okay? Whoever that person is. Who is that person? It's the person in the data set. So this is like saying, what if that person repeated this process? So that one person is repeating the process over and over again. All right. What would be that person's productivity on average? That one person's productivity would be between those two values. Does that sort of make sense? We're looking at that one person as opposed to everyone. The other one is an average for everybody. If for that value of X, here we're saying for that one person, if they did this process over and over again, what would be their sort of average, even though they don't use the word average here. That's what they mean for this particular person. Because somebody might say, well, I know what they did, right? They scored whatever their Y is. That was their productivity. Well, that's in that one day, for example. Maybe if you looked at their every day for a year, right? And it's pretty obvious you probably would average all those days, come up with their productivity, right? But anyway, it would have to be exactly the same X value that's used, and we would look at their Y's over and over again, and then we come up with this. And this would be an estimate here. This range here would be an estimate of what we would think they would score over the long term. The width is a little bit longer, right? The width of the interval. Width of the interval is the low end, the high end minus the low end. That's the width of the interval. 19.528 for the prediction interval, and they didn't even give it here, but you can see it's like it's less than 9, right? It's like 8.5. What is it? 8.562. 8.562 is the length of the interval, and this is longer. It's bigger interval. All right. So read through this. Hopefully it'll make some sense to you, what it means. But this is new, right? And some software programs, the more advanced software programs, do allow you to calculate these things in your data set. You can actually add these as columns in your data set with confidence intervals for each value of X, prediction value intervals for each value of X. You would have both of those there. I don't know if Minitab has that feature, but and then you could even create these pictures, which you could do in Minitab, I believe, where you have different values of X here, your scores on the dexterity, and then you would have not only the regression line, but you would have prediction intervals around each one of these, and you can graph these lower end of the prediction intervals as a curve and the upper end of the prediction intervals as a curve. And these are called prediction bands. You can call them outer bands and of the actual regression line. Shows you sort of like a 95% intervals going across as you change your values of X. Kind of cool. I like that. Does that make sense, that picture? Yeah. So that's the types of pictures you see in regression, things like that. Right. And it does look like Minitab does this prediction. We'll have to see. Let's see if Minitab will do this for us. So, I think they do it. Well, Minitab will give you a confidence interval, overall confidence interval for the beta, right? That's what it's doing here. Although it does say for new observations, predicted values for new observations. All right. So you can create new X's in your data set, looks like, and you can come up with, based on that X, you can come up with the confidence intervals and the prediction intervals. This is where I think the prediction intervals will come in handy, right? Because you don't know what a Y is for a new value of X, right? You don't have it. So you're going to use your Y hat as an estimate, right, of what the Y is. And you can come up with a confidence interval and a prediction interval for that new value of X. All right, so this is where I think you can use these things, and I think Minitab has that feature. All right, so let's try that. So let me stop sharing this and go into Minitab, and we'll open up that data set. Have you already entered that data set into Minitab? Have you done that?
Yeah.
Yes. All right. So I haven't done it yet, so let me just do it. All right. File open. All right. So chapter 15. And just enough. All right. So how did we get to regression? We hit stat and down to regression. Okay. And I believe everything we could do, we could do with regression is right here. So we just scroll down to regression. Okay, and it has fit regression model. I guess we could do that. The response variable is your Y. What is the Y in this case? Is it C2? I think it's C2, right?
Mm-hmm.
Productivity rate. And for the continuous predictor. Now in this case here, both the response and the predictors are all continuous because we're not going to go beyond that. There's all different possibilities with this, but we're not going to talk about that in this course, although it would be interesting to do that. But I think I don't want to confuse you. You could have categorical predictors too, but we're not going to, again, we'll make sure everything is continuous. All right, now let's go through what's down here.
Professor, do you want to be sharing your screen right now? Because we see you at this moment.
You just see me? Well, that's pleasant. Well, why not? You can just look at me and I'll tell you what I'm saying. All right, so Minitab. All right, so let's actually cancel this out. Now, I already entered this, and I think, Rose, you already know how to do that, but maybe I should go out and go back in. So let's go back out and in again. Okay, so give me a second. Oh, I can't minimize. Too bad. All right, so how do I get, go? All right, give me a second here. I'll explore. Oh, let me do that. Think for a minute. I think I probably have to get to Minitab from here. Unfortunately, when you're in Zoom, you can't, when you're recording, you can't exit out. So I have to get to it this way. Minitab. Minitab, here we go. All right, so I'm good. All right. And where are we? All right, so here's Minitab, and then if we want to open, now you have it on your hard drive, I have it somewhere else in my hard drive, so I'm just going to find it. All right, here it is. And opening it up, and then I click OK. In my data set now. Now to get to regression, I'm going to hit stat, regression, And again, regression. All right, because I don't think there's anything else here that will give me anything other than that. And well, it does say fitted line plot. We could look at that in a while. Let's do fit regression models. Response variable is our y. So our y is the productivity rate. And the continuous predictor, the predictor is our independent variable. That is our dexterity score. No categorical predictors. We're only doing one predictor at a time in this course. All right, so suppose we want to do a model. Let's click the model here and see what it's asking us to do. This would we only use if we had more than one predictor. So don't. So we're going to skip that. Options is good. We could weight our observations, but we're not going to do that. That's too advanced. Now, confidence intervals for all intervals. All right, so we could pick a different one. We could pick 99%, 90%, whatever. This is where we would do it. Do you have that in your version?
Yes.
Types of confidence intervals, the only type you learned was two-sided. Sum of squares for tests, or there are different types, but we'll stick with the type 3 here, what's defaulted to. We're not going to do anything else. These things that are here, these are called transformations. We're not going to learn about those in this course. So basically, the only thing that we would change here is if I was asking for a confidence level, if I asked for 99%, you would change it right here. All right, so that's where you would change it. Coding, no, we're not doing that. This would be if we had categorical predictors, but we're not going to do that. Standardizing continuous predictors, no, I don't think we'll do that. Stepwise regression, no. Validation, no. Graphs might be interesting. We could look at the histogram of residuals. That might be interesting to do. Normal probability plot of residuals. Residuals versus fits. I think we'll just do these two here for the time being. A histogram of residuals and normal probability plot of residuals. All right. Click OK to that. Results. This is telling us what we could end up with if we wanted to. Now, analysis of variance, I told you we're not going to be doing that in this course, so I can unclick that. We're going to skip that. That won't show up in the output. Model summary, yeah, that would be fine. Coefficients, definitely. Regression equation, you bet. Like to see that. Fits and diagnostics only for unusual observations. Yeah, I guess so. Durbin-Watson statistic, I don't think so, because we haven't learned what that is, and we won't learn what that is. Right. And then storage, I'm not sure what that is. Oh, storing. Oh. This might be useful, actually. Let me think about what's here. You don't know a lot of what's here. But one thing that we would do when you check a box here is that it actually would create a column in your data set for those things, for each of the values. In other words, for example, you could end up with, you could list all the residuals in here. Instead of trying to figure out what they are, you could actually check this box and it'll actually list the residuals for each observation. The rest of this, I don't think. It says coefficients here. Oh, I see what. Coefficients. Design matrix. We don't want that. I think fits. Let's see what fits will do. I'm not sure what that does. Let's try fits. All right, I'm going to click OK here. Let's see what happens. You know what the fits are? That's the y-hats. So it does the calculations. So this will be useful for you, won't it? it can give you what the y hats are for each one of the values of x's, for each value of x, based on the regression equation. Now, what's the regression equation? This is the one up here, right? This is what's in the book, right? This is your slope 3 and your y-intercept 19.2. So if you plugged in 12 into this equation, you get 36 plus 19.20, which is 55.2, and you can see that's what shows up here under fits. See it? Under here, fits. So the fits are the y hats. The residuals are the difference between the y and the y hat. It does the math for you. You see it in the down here in the table. So it gives you those values in the table. All right, now let's see. Change the. One second here. Something is, don't see. All right, let's just scroll down. Now, let's scroll back up. Let's show you what's here. So we have the equation. Here are the coefficients. All right, when it says constant, that means the y-intercept. It'll actually name the dependent variable for the coefficient for that variable. Now, this only makes sense if you had multiple predictors. If you had like 20 predictors, right, for the y instead of one, each one of them would have its own beta. And then the way to recognize the beta for that predictor is what predictor variable is it multiplied by? And the answer in this case, of course, would be dexterity score. But if there was another one, another predictor, and another predictor, maybe age could be a predictor, who knows? So it would have its own beta like that, all right? But we're only dealing with one predictor or independent variable, and that's why it's called dex score. It's not referring to the x, it's referring to the beta that's multiplying that x, the slope. So beta is 3. Here's the standard error for that beta of 3.541. The t here, how did they get this t? Well, the null hypothesis is that the beta is equal to what? 0. The alternative hypothesis is different than 0. Okay, so the coefficient minus the beta, the null beta value, which is 0, so it's 3 minus 0 divided by the standard error gives us the t. So 3 divided by 0.541 is 5.55. That's where they come up with that. Okay, this is the way you calculate these. And then it would be then of course you would, if this is a 95%, right? Remember, we set it up for 95%. If this is a 95%, how would we say this? If it's 95% in the middle, that means it's 5% alpha. All right, they're assuming a 5% alpha here. Now, 5% alpha would mean what? 2.5% to the right, 2.5% to the left, right? So if you did a t with how many degrees of freedom? 3, all right? And found the probability. Let me actually do this on my calculator. I just want to double check to see if Minitab's doing this correctly, at least the way I think they're doing it. Give me a second here. Yeah, okay. So when you do this with a calculator, you're going to get the right tail of the two-tail test. This is a two-tail test, right? Because alternative hypothesis is beta is not equal to 0. So that's two-tailed. You find the area to the right of 5.55, because the null is 0, right? It's to the right. The area is 0.00577. And then you multiply that by 2, you get 0.0115, which rounds to 0.012. So there's your p-value. All right? No different than calculating any other type of p-value. You get your t. It's a two-tailed test. You find the area to the right because it's bigger than 0. And you multiply it by 2. And that area, and you end up with 0.012. And then if alpha is 0.05, all right, the alpha is 0.05, we reject the null hypothesis and say that this slope is significantly different from 0, which is what we want if we're going to use it for predictions. What if we ended up with a p-value of 0.4 or 0.5? Would we use this data in a prediction? Would we? If the null hypothesis says beta 0 and we get a p-value of 0.4, not 0.012, that means do not reject the null.
Right.
Would we use this equation?
No.
No, we wouldn't. By the way, what would we use for y if we did, if x is, if the beta, the slope is found to be not significant? What would we use for y? What would be the best predictor of y then?
Just 19.2.
No, well, that's the y-intercept. But if we wanted to predict y, no, we can't use that equation at all. We can't use that equation at all. So what will we use instead? How about the mean of y? The mean. If we're going to predict what y is, and x is not significant, we might as well use the mean of y as the best predictor for y. Isn't that what we do in statistics anyway? We want to predict a y, like the population mean. What do we use? We use the sample mean. So we might as well use the sample mean as the best predictor for any of the y's. If x doesn't predict, right? If x doesn't predict it, what are we going to use? We might as well use the mean of y. And that's typically what they say. Don't use 19.20. 19.20 is only there as a filler for that equation. It's meaningless without the dex score, without the 3 plus 3 times the dexterity score. That's 19.20 is meaningless otherwise. It doesn't play a role. What you were basically saying is 19.0 if we assume dex score is 0. But that's
Right.
using that, but that's using the equation. The significance, if this test here is saying it's not significant, this whole equation's not going to be used, the whole thing. So what I'm saying to you is that the best predictor for y is the mean of y. The actual mean of y would be the best predictor. If it's not dependent on x, what else is going to be dependent on? We don't have any other predictor variables. The only thing that we can use is the mean of y as the best predictor for y. Because the mean of y represents all the y's, right? Doesn't it? Since the mean of y for the sample estimates the mean of y for the population, and the mean of the y for the population is the best representative of all the y's in the population, we might as well use the mean. That's the best thing we could use. Unless we plot the y's, which we can, right? We can do a histogram of the y's, right? We could do that. And if the y's are skewed, we could use the median too. The median of y could be an estimate also, right? If it's skewed. I mean, we could do that too, right? With Minitab, we could simply, what would we do? We would do, find the histogram, we would graph and do a histogram, right? And we use the y as the variable for the histogram, and we would look at it. Does it look normal? Does it look skewed? If it looks fairly normal, we'll use the mean. If it looks skewed, we'll use the median. That's a possibility too. All right. Well, here's a histogram, but this is a histogram of what? Residuals. Residuals. All right. All right. I don't know if that's very useful. I don't even like it. But this is useful. This is useful. This is called the normal probability plot. It's in this chapter, by the way. If you plot the residuals, right? If you plot the residuals in here, and it says percent, all right? So along here is some sort of frequency. Plot the residuals here, and if you can draw a straight line pretty much through those residuals, that means what? It means that the residuals are normally distributed. That's one of the requirements of this. And that also, by the way, probably means that the y's are normally distributed. All right. This plot here tells you quite a bit. If we see a straight line, this indicates normal probability, and this is what we use for one of those three requirements for regression. Remember the normality? Yeah. So this is one way of finding that. All right. Let's see if that was it for graphs. We're not going to spend a whole lot of time on that because this is an introduction to it. Now, what do we do to get the confidence intervals for each value of X and the prediction intervals for each value of X? All right. So what do we do? Now, in the book, this is an older version of Minitab. All right. It says on the add-ins ribbon, click Data Analysis Plus. All right. Well, that's in Excel. Let's see in it says options. Select options in this. All right. Now, where are the options? Let's see. Close. That's not options. So where is options? Anything in here for options? See anything? Let's go back to regression. And let's here's something, predict. All right, so we have regression, and do you have something that's called predict in here?
Yes.
All right, so let's try it. See what happens. All right, so it gives us our y's, right? It automatically puts the y in there for us. Enter individual values. Enter columns of values. So what do we put in here? Our x's, probably, right? Dex scores. So enter columns of, so we'll say Dex score. So I don't know if that works or not. Well, let's try it. Click options here. Tells us the confidence level for our predictions. All right. Results. Prediction table. I guess you can create a prediction table here. You can also do regression equation. Let's try the prediction table. Storage. Here we go. Under storage, they have confidence limits, prediction limits. They give you the standard error of the predicted fits. All right. Standard error of the predicted fits. What is that? That's the square root part of it, right? Probably times the other thing. Let's see. Let's try this. Click OK. See what happens. All right. Now it looks like what did it do here? It didn't give us predictions for each value. It didn't, right? Gave us an overall fit. That's not what we wanted. So let's try this again. I want to X this out, by the way. I don't like it. All right. And all right. Well, look, it did give us the values. Here they are, right down here. So let's look at them, see what happens. All right. CL, of course, is confidence limit for what? This is lower, upper, maybe, maybe. So it gave us a confidence interval for the first value of X, 12, between 49.9811 and 60.4189. Okay, and it gave us our prediction interval. So this is our confidence interval, 95% confidence interval. And this here is, for each value, is our 95% prediction interval. Okay. Now, what is this thing here? PSE fits. What the heck is that? So let's go back. Look at the confidence interval for X is equal to, now, one thing we didn't do here, we could put in a value of X in here and it would give us a predicted value of Y, right? We could do that. We could have entered another value of X in here and it would have given us our limits here. So how do we know what this PSE fits is? Is that standard error? Would that be the standard error? I don't think so, right? 1.6, like the first line here says 1.63989. That can't be the margin of error for sure, right? Because what is our Y hat? 55.2. 55.2 is the Y hat for when X is equal to 12, right? 55.9, 55.2. 1.63989. What the heck is that?
I think it's standard error of predicted fits.
Okay. So why don't we do something? Why don't we take the formula? Let's try it out. I think we have time. Let's try out the formula for use the confidence interval one first. And let's calculate, first of all, what T is for this situation. I think we already knew what it was, right? Did I tell you what it was?
Which one?
What's the T? Well, we don't know what is the T situation here, the T that we're going to use. Critical T. Maybe we didn't do that, right? We didn't figure it out. Look at the formula for confidence interval. Page 563. Okay. I want you to figure out what this 1.63989 is. I want you to figure out what that is so I want you to figure out what the standard error of the estimate is, which is going to be the same. Standard error estimate is going to be the same for each one of these values, isn't it? That's the formula on page 561. Tell me come up with that for me. Tell me what that, with your calculator. For this situation here, can you tell me what the standard error of the estimate is? Let's do that first. Can you do that? Am I asking too much?
So you want us to add all the values up and yeah, okay. I can try.
Well, the residuals, I mean, you could put these into Excel, right? I mean, we know what they are now. These values here. So put the residuals, just type them into Excel, square them, right? Because column, the C4, here's your residuals. Square each one of these, add them up. I even think that they even did this for us, didn't they? Yeah, on page 562, you'll see it. They did the calculation for us. 2.757 is our standard error. Correct?
Could you repeat that, please?
Page 562. They already did the calculation for us.
Hmm.
Right?
Yeah.
Yeah, it's there. So I want you to figure out what this 1.638989 is. All right? I see it, but I'm not so sure what that is. So I want you to figure out whether now we know it can't be 2.757 because that's true for each one of those x's. That's the standard error of the estimate. That's in each of the formulas. The t is going to be the same too, right? The t is going to be the same. Now you have to find the t critical value using inverse t. So find what t is. We know what standard error of the estimate is, and then do that square root calculation. Do it for the very first one here where x is equal to 12. All right? Can you try that?
The standard error of the estimate.
We have the standard error of the estimate.
Okay, which one did you want us to get?
All right, I want you to confirm what this, in line 1 here, I want you to confirm what this 1.63989 is. What is that referring to? Hans says she thinks it's something, but I want you to verify what it is. What is that? I want you to verify. Tell me where that came from. Now, if you look at the confidence interval and prediction interval for this problem, they give you what the numbers are, by the way. They tell you what the sum of x squared is. They tell you what the sum of x, what x is. You don't have to do anything in Excel. Just use your calculator. The only thing you have to replace, like on page 563, it's a 15 with 12 inside the square root. I hope you're following what I'm asking you to do. I want you to figure out what that 1.63989 is. You're completely lost, I say.
I'm lost.
Look at the formulas on page 563 and 564. You're looking at your book?
Yes.
All right. Those are the formulas for the square roots. All right. Are we good with that?
I don't have the t value. How do I get that?
No. Let's forget about the t value. Well, that's inverse t. That's critical value. I told you how to do it. Inverse t with the, you know how to do it. I mean, you take your, it's the inverse t with 3 degrees of freedom. Inverse t. Use Excel or use your calculator, whatever you have. Use your Excel. Do an inverse t with 3 degrees of freedom. That's all.
For which value?
You don't need a value for inverse t. It's 3 degrees of freedom. It's a critical value. That's what the t represents. Critical value. It's a 90.
I'm lost.
All right. You're not sure how to do an inverse t?
Well, for inverse t, it asks for a probability and then degrees
Yes,
of
for an
freedom. I
area.
have
Right.
degrees of freedom.
So if it's a 95, if it's a 95% confidence interval, and then the area to the left is going to be 0.975.
Right. Okay.
Yeah. See, what we're doing in this problem is integrating things we learned from the past. And I get you're confused because you're not making those connections yet. You will make those connections, all right? There's no ifs or buts about it. Han, do you understand what I'm saying? Inverse T? You don't? You don't know, for a confidence interval, you don't know how to find a critical value? You learned it in test number 2. Or actually, you haven't learned it yet. It's in the homework. I think it's in the homework, right? When you're coming up with your confidence intervals. You need critical values, right?
Is it using the Excel,
Yeah, use Excel.
like equal T dot
Look for the inverse one.
inverse?
Yeah. And the area to the left is going to be 0.975 if it's a 95% confidence interval. That information, that knowledge is the same here. It's not changing. It's just the degrees of freedom is different. It's 3 degrees of freedom here instead of something else.
So it asks for probability.
That's the
That's
area
not-
to the left, area to the left,
So
area to the left. If you have a 95% confidence interval, it's a 95 in the middle plus the 2.5 on the left.
Right.
Okay, so it's 97.5. You get like about 3.282, something like that, 3.182.
Yeah, that's what I got.
All right, so that's T. We know they've already done the calculation for you on page 562 for the standard error of the estimate, which is 2.757. Okay. By the way, if you look on page 563, you multiply the inverse T number times 2.757, you get the 8.773. You see that?
Yes.
Yeah, that's where they're coming up with that. I mean, they use 8.773. I see 8.774, but that's where they're getting that from. Now, the square root is what's inside the square root, but what I want you to do is pull out the 15 and put in the 12. Right? Because the value of x for the first line in here, I want you to use 12 instead of 15 because x is 12. All right. So in that square root part of the formula, I want you to put in the numerator of that second term 12 minus 14 quantity squared. Okay.
Mm-hmm.
All right. So put in 1/5. You know how to do that with your calculator. You just hit 5 and then X to the -1 button will give you 1/5. And then plus, and put it in parentheses. Well, I think you could do this in your head. The numerator is going to be 12 minus 14 is -2 squared is 4, right? So the numerator is going to be 4. And the denominator, I believe, stays the same, right? It's 1006 minus 70 squared divided by 5.
Okay, I have an answer. But do you want it in the form of in the square root or just the answer?
Yeah, what did you get with the, what are you going to add and subtract to the 64.2? Well, the y hat in this case is not 64.2, right? The y hat is what? In line 1 here. The y hat is 55, right? or 55.2. 55.2 is the y hat. So you're going to add and subtract from 55.2 what number?
8.77 times the square root of 0.3538. Does that
Okay.
agree with yours?
Well, I didn't figure out what's inside the square root, but I get, when you multiply those two, I get 5.219. If my
Yeah,
arithmetic,
that's what I got too.
yeah. And if you add and subtract that from 55.2, you should get those confidence limits there, to 49.9811 and the 60.4189. Okay. Let me just double check that.
In their solution, where did they get the 62.4? Is that related to something from our data set, or is that just a different value?
Well, y hat is for x is equal to 15. That's what y hat is.
Oh,
Right? If you plug in 15, you get 64.2 into the
okay.
regression equation. That's y hat.
Got it. Okay. Okay.
Yeah, yeah. Okay. Now I come pretty close to the lower limit of 49.9811. I get 49.9808, pretty close to what Minitab comes here. And then if you add that 5.2192 to 55.2, you should get pretty close to the 60. I got 60.4192. They got 60.4189. So that's good. I think we just confirmed the confidence limits there, confidence interval. Are you okay with what we just did?
Yeah, sort of.
Yeah. And you could do the same thing for the prediction limits. The problem I'm having is with this PSE fits here. What the heck where are they coming up with that from?
I'm pretty sure it's the standard error of the predicted.
Uh-huh. Let's go back.
Because if you go to the regression, predict, and hit the storage, it has standard error of predicted fits.
Yeah. So what you're saying, I think, let me see if I understand what you're saying correctly. I think what you're saying now, Steve, what did you say? What was inside the square root again?
Oh, the number?
What was that number again?
0.3538.
Okay, 0.3538.
That's what I had, yes.
Now, if we took the square root of that, I get 1.1635 for the predicted interval. Have to add 1 to it inside the square root. So now, that doesn't match the 1.63989. That's the only problem I'm having, is I'm not sure what that number means. I'd have to look at the documentation, I guess, for Minitab. I don't think that is what's inside the square root for the prediction interval. Because if you're right, 0.3538, then the prediction interval square root is just 1 plus that, right? Yeah, and if you take the square root of 1.3538, you get 1.1635. And that's not 1.63989. So
Would
go ahead.
we use? Can we use the formula on page 561? The standard error
let's
of
look.
estimate.
Let me see. Yeah, but that number is not a number for each value. It's an overall number. 2.757. All right, but you explain to me what you mean by that. Go ahead.
No.
No,
I
I don't think that's what it
I
is
didn't
either.
have a clear thought.
So I'll have to investigate it. Obviously, we're not going to use it. This thing here, what I just showed you, the PSE fits, there must be some formula that is involved with that. And I'm not so sure whether it is anything that we're learning here. So I'd rather not use it. I'm just telling you, I wanted to see what it was first before, and it doesn't seem like it's anything, any of these formulas that we're using. All right.
No.
Yeah, so let's skip that. All right. And remember, it was a box we checked to get to that. Don't check it. It's just going to confuse you. I'm not even sure what it means. I'd have to, investigate it. But certainly I don't want to teach something that's not in the book. So we'll skip that. What is useful is everything else that's here. There is the confidence interval and a prediction interval for each value of X. All right. And if we wanted to, by the way, if we wanted to, we could have entered an additional value of X into here. And let's say we wanted to come up with a confidence interval and a prediction interval for a particular value of X, or a prediction interval for X is 15. How would you do it? You would enter 15 as an additional value in C1. Then you would come up with a fit for it, right? You can do that, right? The fit. The fit is the y hat. So it'll do that for you, give you what y hat is. You'll know what now they won't give you a residual, but do you need a residual?
No, the residual should be 0, right?
There's no residual in this case, there's no y. If you're picking a value of X that's not in the data set, you're not going to get a residual. But what you will get is a prediction interval and a confidence interval, because the prediction interval and the confidence interval, let me double check, hold on. You have to be very careful with this, because let me just double check something here. It's saying the mean is 14 for X, right? Mean is 14. So the values of X that we, yeah. And 26, 43, 59, 70. So the sum of the X's come out to 70 divided by 5. And that's 14, right? So here's the deal. You have to be careful with Minitab, because if you plug in an extra X in there, it may give you, they may average that into X, the average of X, and that's not what you want, right? In this formula, the average of X is based off of the other X values, not the new value of X that you're using. So I think you have to be very careful here. I think you might have to do this by hand. This formula that you see, if we have a new value of X other than what's in here, I'm pretty sure. I have to test it out, but I'm pretty sure it would average in the X, the new value of X, in with the other values of X, and that's not what you want. So I think to be safe, you can use Excel, obviously, for this. But if you were going to plug in a value of X into one of these confidence interval or prediction interval formulas that is not in your data set, you may not get the proper answer. And actually, all of these might be wrong, because it'll average in all the X's. It might do that. So I don't think you should add in if you had a value of X that's not in the data set, I don't think you should add it in here, because you may end up with screwing up all your answers. And it's probably better to do it in an Excel, so you could be safe. And see what I'm saying? The value of 15 that's in the example on page 563, that 15 is not part of X, the mean of X. But if you put it in here, it may make it part of X, the mean of X.
Right.
So, yeah, so just to be safe, especially when I give you your project, you don't want to put in an additional value of X in here. Some computer programs allow for that, and they will not, that it'll recognize that as an additional X that's not in the data set. I'm not so sure whether Minitab can do that. So to be safe, I would, if I was going to do a confidence interval for a value of X that's not in the data set, or a prediction interval, I would do that in Excel and not here. All right, just to make sure that you're not averaging in that new value of X. All right, so it's 10 after 10. Let me ask you a question. Do you think you have a better idea of what's going on with regression, or was the whole thing very confusing to you? I mean, it's possible it was confusing.
I think I do know more, although I was confused at certain points.
Uh-huh. But you now know where to go for predictions. If you were going to predict, or you're going to have confidence intervals or prediction intervals for a value of X that's in the data set, you can do it here.
I believe so, yes.
Yeah. But as far as fitting the regression, when they say fit the regression model, that means to come up with the see, it's actually putting in all these values in here now, all these variables. But as far as coming up with the equation, this is where you would put it in, right here. I mean, this is where you would get it, right? And that, you know how to get there now, right? Stat,
Yes.
regression, and then regression, and then fit regression model. So when it says fit, it'll actually calculate it for you. That's what, and then it'll give you the coefficients, which means the y-intercept and the beta, the slope. Now, one other thing I wanted to mention to you before you go, because this is mentioned, we know what correlation is. We went through correlation last time, correct? We did, right? Yeah. Something that is kind of looks like correlation, but isn't quite correlation, is called R squared. R squared. And let me just point out to you where you could see R squared. It is it's on page 569. Now the equation for R, or the coefficient correlation, is on page 568. Now, it doesn't tell you here what the correlation coefficient is. It doesn't give it to you here. Except if you go to statistics, basic statistics, and scroll down, you'll see correlation. See it? You go to statistics.
Yes.
Basic statistics, and then scroll down to correlation. And then you can type in the two variables that you want the correlations to be about. So in this case, it would be C1, C2, right? So C1, actually, you could probably highlight both of them and select. Okay. Then click OK. Now it actually does a dot plot, and what they call a matrix plot, but it's sort of like a dot plot. But here's the correlation right here, 0.955. By the way, you could do a confidence interval for correlation too. And it shows you how to do it in this chapter. Come up with a correlation, a confidence interval for correlation. But it gives it to you right here between the two variables. And here's the correlation, 0.955. Strong correlation between those two variables. A correlation does not imply causation, but it does say those two variables are closely related, right? Now, what is R squared? Let's go back to the regression. Now remember the correlation is 0.955, just so that you remember that. Look at R squared, 91.12%. If you take 0.955 and square it, what do you come up with? Pretty close to what they're showing here, right?
Yeah.
Yeah, pretty close to it. That's because probably 0.955 is not exactly correct. Probably more decimals to it. It's an approximation. But this is called R squared. Now, for a simple linear regression, this is not true for more than one predictor variable. We're only dealing with one predictor variable. Only for one predictor variable can you take the correlation and square it and get R squared. What R squared is, it's a measure of the following. It takes the regression model and says the following. It says, how much of the variation of Y is explained by this regression model? And in this case, it's a very high percentage, 91.12%. If you look on page 569, it gives you a formula for calculating R squared that is not the correlation coefficient squared. It gives you the exact formula, which can be used for any type of regression model. And it's simply the numerator, it says 1 minus, and then it gives you a fraction. If you look on page 569, the numerator of the fraction is the residual squared divided by what's called the sum of the total sum of squares. That is the sum, that is each Y, the deviation of each Y from the mean of the Y's squared. You add up all those deviations of the Y from its mean, you get the total sum of squares. That's a total variation of Y. If you divide the total residuals, which is the errors, divided by the total sum of squares, that's sort of the fraction of the variation that's unknown. The errors, right? The errors are unknown. And 1 minus that is the percentage of can be explained by the model. Does that sort of make sense? So when it says R squared is 91.12%, that means that fraction, 1 minus that fraction is 8.88% when you divide those two numbers. That's the unexplained percentage. That's the so-called error in the model. And the amount that's explained by the model, the regression model, is 91.12%. So many times people will ask about what's the R squared, and typically you want a high R squared. Now there's a thing next to it called the adjusted R squared, and there's a formula that's on page 370 down on the footnotes. All right, and that adjusts for how many predictors we have in the model. Now in this case we only have one predictor, but it does make a little bit of an adjustment. Some people use that instead. Now I'm not going to ask you to do anything with something that's in the footnotes of any book, but I will tell you that if you do take statistics later, more advanced courses, you will need to know about the adjusted R squared, because that's typically what researchers do use. And that's because you'll have models with many predictors, not just one predictor. What this other term is here, I don't know what that is. I've never seen anything like that before, but R squared and predicted R or adjusted R squared, I've seen that. But just know what R squared means, all right? And if I give you that number, you can explain it in a sentence what that means. That the model explains 91.12% of the variation of the dependent variable, which is what? It's the productivity, right? the variation of productivity rates can be explained by just having this dexterity score in the model. A lot of it's explained just with the one predictor. Many times you'll see R-squared much lower than that. That might mean that you may need to add some additional predictors in the model. All right. So, and then the last thing is, I told you about the test for the, you go back to the correlation. Go back to that. Remember, it has a confidence interval here. It explains on page 572, 5 to 574, or 575, explains how to do the hypothesis test for a correlation. Explains how to do that. All right, it has a special standard error for that. All right, so it's all explained in the book if you're interested in that. So what we're going to do next time is we're going to actually pick some other data sets in here, and I'll go through with you. Hopefully, all this will become clearer to you. We'll go through the different steps of doing a regression analysis in the limited way we've done it. I mean, we haven't done very much. You might think it's a lot, but we haven't really done very much in terms of what typically is done in regression. But we'll go through an initial analysis. I'll tell you the types of things I'll ask you, and then I'll explain what your project is. All right, because I'm going to give you a data set for the project. You won't know about it until I send it to you, and then I will ask you questions about that. So you're going to put it into Minitab. You're going to run you're going to fit the regression. You're going to find out the correlation. You're going to find out the R-squared. You're going to find out what the equation of the line of best fit is, all those sorts of things. And then I might even ask you for a particular value of X, what's the predicted value of Y? Give me a prediction interval or a confidence interval for that value, something like that. Those are the types of things I can ask. Make sense?
Yes.
Okay. And believe me, I'm not going to give you anything that I didn't sort of explain tonight, but we'll explain more of it next time. All right. So for the time being, finish your homework. Forget about regression until Thursday. All right. And finish your homework. Get the homework done and send it to me by tomorrow night. And then Thursday, we're going to do several questions, and we'll start at 6:30. That way, we'll have plenty of time. I mean, tonight's meeting is almost 2 hours. It will not be 2 hours next time. It'll be an hour and a half, because I will have specific problems we'll go through. All right, and I'll send you the data sets, the Excel data sets for those. All right, there'll be problems that may come up in your textbook that may require a Excel file, and I'll post those and send them to you. All right, post them in Canvas. All right, sorry about it being so late, but a little bit of a crunch here at the end. Do you have any questions? Probably many questions.
I can't think of any right now.
Yeah, it's a lot. It's a lot. Try to do this all in one night. It's a lot, but I wanted you to become familiar with how to use software, right? This is where the software comes in. You don't want, if you have a fairly large data set, you don't want to be doing this by hand. You don't want to be doing, even Excel might be, like I said, for a particular calculation, Excel might be useful, but you want statistical software to do a lot of the number crunching for you, especially, coming up with confidence intervals and prediction intervals for every data value for each X in your data set. If you have, like I said, if you have 1,000 of these, it would take you forever, right, to do these confidence and prediction intervals, and it's done in a snap with Minitab. So we're going to do this again. Everything I did tonight, we're going to do some more examples, and by the time, I hope by 8 o'clock on Thursday, you'll be clear about exactly what you need to do for both the project and for the exam coming up on Tuesday. All right? Any questions? All right, so I'm
No.
going to let you go. Again, I apologize for being so late. And Rose is probably going to kill me for making this so late for her. All right. So anyway, I will see you on Thursday. And again, put this out of your mind for now. Just work on the homework for the other 3 chapters, and then we'll be there's not going to be homework for this chapter 15. All right, it'll be that project that will be the so-called homework. All right. Okay. You guys look tired, so I'm going to let you go. I'm not tired, actually. I'm kind of wound up. So when you teach, you don't get tired from it. You get wound up. So it's going to take me 2 hours before I can go to sleep now. I'll have to probably watch a movie or something to wind down. All right. All right. I'll see you guys on Thursday. Remember 6:30, and I'll send you the link earlier in the day on Thursday. Okay.
Okay,
And if
sounds
you have
good.
any other questions about your homework, do send them to me. I'll try to get them answered also. All right. But you're
All right,
okay
thank
with
you.
the homework so far? I mean, you got most of your questions answered now?
Yeah, yeah. I just have, well, I want to go back to the last question in chapter 10 and then do the chapter 11 questions. But yeah, so far I'm always paranoid about accidentally putting the wrong number in. So it takes me a long time to go through it, but I'm getting there.
Okay. Well, don't worry. I don't deduct too much. It's like Han, I was explaining to Han also, as long as you show me your work, I'm not
Mhm.
going to deduct too much if there's a little bit of an error or something. So don't worry about that so much. It's the reasoning that you're doing behind it. That's more
Okay.
important than making a silly math mistake or something. So don't obsess too much. I mean, I want you to get the right answer, but I don't want
Right,
you
yeah.
to stay up to really late because your answer, you're not sure if the answer's right.
Okay, all right. I will take that advice.
All right, good. Okay. All right, I'll see you guys later. See you on Thursday.
All right, have a good night.
You too.
Good
All
night.
right. All right. Bye.